I'm sure that that's going to be fine. And all right, now everybody at home, type again. And I'm really sorry about that. All right. Did you get it? Yes. Okay. All right. Can everybody see the screen at home?
Yeah.
Yes.
All right, good. Thanks. All right, I do not know why it's doing that. Why are you doing that? Can I just, I'll just do that? There, okay, that's what I want. All right, so today we're gonna take this a little further. We've established that populations have growth rates, that they are either geometric or exponential, that they don't grow indefinitely, that they will level off at a level that's set by the available resources in the environment, and that's the carrying capacity, or K. And today we're going to talk about when populations are either stable or unstable around their carrying capacity, and try to enumerate some of the reasons why you see populations either pretty close to their carrying capacities most of the time, or far away from their carrying capacities a lot and fluctuating around something that you could approximately say was a carrying capacity, but which the population is usually not at. So first, we're going to look at the patterns that we're going to try to explain, and we're going to try to understand what it is that happens in nature, why the logistic equation is not good enough. Then we're going to talk about density dependent factors versus density independent factors. We talked about density dependence last time when we talked about going to K. Density independent factors are an important reason why populations fluctuate around their carrying capacities. Then we'll move on to talk about something that is particularly important to discretely growing populations, showing geometric growth, and that's the effect of variation in the growth rate, and how that causes instability in populations. We'll then look at a fourth thing, density dependence, but delayed density dependence. And we'll explain what that means, but that's an important reason why both exponentially growing and geometrically growing populations may show instability. And then finally, we'll talk about something that's really actually quite important, but doesn't get a lot of press, and that's stochastic population growth, where we have a lot of random variation in things in the life table. So this is not a calculation type lecture. We aren't going to be calculating things, but we are going to be showing you graphs and trying to get you to relate these concepts to what you see on the graphs. And I'll expect you to be able to look at a graph on the exam and say, oh, that could be because of one of two things, either this or that, and explain why that is. So here, first, let's just look at the patterns that we're trying to explain. First, we've got populations that are stable around their carrying capacity, and they may fluctuate up, they may fluctuate down. If they go over carrying capacity, then growth rate becomes negative and they return to K. If they go below their carrying capacity, then growth rate returns to positive. It gets, it's at 0 at K, or 1 if it's geometric, but it then increases and they go back to K. So they're more or less stable. Okay, and that is typical of species that are large, have long lifespans. But then there are other things that we see in nature. We see populations that have regular fluctuations. So sometimes they are above carrying capacity, and then other times they're below, and they're above, and then they're below, and there's a period to this. So it's kind of like a sine wave. Then we've got populations that show irregular fluctuations that are just kind of all over the place. We've got populations that appear to kind of drift randomly and gradually, and they don't have sharp increases or decreases, but they just wander around and they're not necessarily near their carrying capacity. Finally, you may realize that the model that we came up with last time, the logistic population growth model, doesn't allow for extinction. And yet we know the populations go extinct. So we need to be able to have ways of modeling all of these things in order to have a satisfactory understanding of nature. So we can't just stick with the logistic growth model. We have to modify it, or at least try to understand why it doesn't often predict the dynamics of some populations. So these are the things that we need to try to explain, and we're going to try to explain them using the things that we outlined on the first slide. So the first thing then is density-dependent factors like competition, predation, diseases, parasites, right? All of those things likely increase as population density increases. And as they increase, the population growth rate decreases. So you have density dependence. So these are factors that kind of put the brakes on population growth gradually as it grows towards its carrying capacity. And although you may have random fluctuations, you're usually quite close to your carrying capacity. So this little graph shows you the dynamics of the population of red deer on the Isle of Room in England, and notice that the carrying capacity is around 300. Sometimes it's above, sometimes it's below, but it's never far from 300. And you can't really say that these fluctuations are wild or that they're regular. There's no oscillating pattern here, no sine wave. So when density dependent factors like competition, predation, disease, parasites, when those things are operating, populations tend to be relatively stable around their carrying capacity. Large, long-lived organisms tend to show this. But of course, not all organisms are large or long-lived. So here's some irregular fluctuations, and here's just an example. The graph is months of the year, and these are phytoplankton cells in a sample of water. So notice that it's really hard to see where a carrying capacity might be here. It's really sort of not clear what carrying capacity might be. And you have some really sharp increases. You have some population crashes like over here. And this obviously is not being driven by these clean density dependent factors that tend to allow populations to grow slowly towards K and then cause them to smoothly level off. Okay, so Lake Erie phytoplankton are not regulated by density dependent factors. What are they regulated by? Well, these guys are, and can I move this to the top? I wonder. This has been bugging me. I want to move this to the top. There. Let's move it to the top. Abiotic fluctuations, like sharp temperature drops when a cold front moves in, they cause mortality of the algae. And it doesn't matter how many algae are in Lake Erie. If a cold front is going to cause 90% of them to die, it doesn't matter if they're 10 per cubic centimeter or 10,000 per cubic centimeter. If it's 10, then 9 out of 10 will die. But if it's 10,000, then 9,000 out of 10,000 will die. So that is independent of the density. The effect of some factors in the environment is independent of the density of the population. Okay, and we typically talk about this in terms of disasters, like freezes, fires, floods, the 3 Fs. Okay, and you have direct experience of density independent factors in your own lives, because you know in New Orleans all summer long you are plagued by what in your backyard at night? Mosquitoes. When the first cold front comes through, what happens to the mosquitoes? They all die. And it doesn't matter if you've got 100 mosquitoes in your backyard or 100,000. 99% of the mosquitoes die. That's an independent effect. It's not related to the density of the population. So populations can be regulated by density independent factors. And if they are, they may show real wild fluctuations in the density. They typically are small and short-lived organisms, because long-lived large organisms can either run away from disasters, and so their populations are not affected, or, for instance, in a freeze that's going to kill 99% of the mosquitoes, it's going to kill exactly 0% of raccoons or deer, because they're big enough to be buffered from the environment. So large species are relatively insensitive to these density independent factors, whereas small species tend to be very sensitive to them. And since they're small and short-lived, they reproduce quickly, right? Because we know that they generally are selected. So when they do have a crash, like here in the graph, they tend to be able to reproduce quickly and recover quickly. So you get sharp rises and sharp declines in these small, short-lived organism populations due to density independent factors. And remember, the 3 Fs are a good rule of thumb for thinking about the things that may be density independent: fire, flood, freeze. It's going to kill a lot of organisms regardless of how many of them there are. So it's density independent. Oop, and now I can't advance. Where's there? Okay, let's advance. Okay, so let's look at populations that may have experienced density independent factors in their lives. We can often figure out that a population has had some density independent something happen to it by looking at the life table, because that's the classic time when you get these big bulges or these big deficits in the number of individuals that you might expect in an age class. So here you have a population of fish, okay, and these are white fish, and notice at the top you have what looks like a kind of a clean bell-shaped curve in 1951. But look at what happened way back 5 years previously in 1946. Okay, you had some reproduction, and actually this is reproduction from 1944 because these are already 2-year-olds. But then look, the ages 3 and 4 in 1946 kind of match ages 3 and 4 in 1951. But look at what happened to the 2-year-olds. They survived way better than you would have expected. And they continued to survive way better because there are just tons of them all the way through to their deaths. So there were many more individuals in that age class than you would have expected. And you can tell that looking at the life table, because in the absence of that age class, 3 and 4-year-olds look very similar in 51 and 46. Something happened so that these guys survived way better. This is really the fingerprint of density independent factors. They had a really good year. Conditions were really extra favorable, and they just survived a whole lot better. So we can often put our finger on the year that something like that happened, in this case, it would have been probably 46, 47, that allowed the 2-year-olds in 46 not to die off the way they normally would, but to survive way better than you would have expected. That's probably something that was a density independent event. And I don't know what that would be for this fish. I don't even know. I think whitefish are freshwater fish, so maybe it was a particularly good rainy year or something. I don't know. But its effect was independent of the density of the 2-year-olds. Okay, let's move on to the kind of third thing that allows us to model real populations, and that's variation in population growth rates. Now, this is particularly important for geometrically growing populations. And I'll try to explain that on this slide. So what we've got here is two populations that are growing kind of at the same rate and kind of to the same carrying capacity, but one of them is growing geometrically, the other is growing exponentially. All right, so on the left, the geometrically growing population has a reproductive event once a year. And so in year 1, here's your reproductive event, and you've increased like that. Year 2, year 3, year 4, year 5, year 6, and then notice that in year 7, this population overshoots its carrying capacity. Contrast that to the pattern in the exponentially growing population. You get a smooth increase, kind of as best I was able to draw using my graphics program. And then you get a smooth leveling off at the carrying capacity right here. Okay, so the exponential population didn't overshoot. The discretely reproducing population that shows geometric growth did. Why? It's because density-dependent factors are operating continuously on the existing population size in the exponentially growing population. So you get a small increase from, say, year 5 to year 5.5 in the exponentially growing population, and that small increase causes a small increase in the strength of density-dependent regulating factors. So competition goes up a little bit. And it's like smoothly applying the brakes in your car to slow down gradually. Exponentially growing populations slow down and approach their carrying capacity very smoothly because there's a continuous, smooth increase in density-dependent regulating factors. Competition goes up a little bit at a time and it goes up continuously. That slows the population growth a little bit at a time, continuously. Contrast that with what's going on in the geometrically growing population. Okay, you don't get that smooth application of brakes. You don't get the smooth slowing down due to competition. Okay, competition is increased in year 6 right here relative to year 5. But notice that there was no change in competition during year 5 because this was your population effectively all year. And then all of a sudden you got this big jump. So you're being regulated in year 6 this way, and you're not getting the increase in density dependent regulation that you would if you were growing exponentially. You're being regulated at this level, which allows you to reproduce this much, which causes you to overshoot. So discretely reproducing populations are inherently vulnerable to overshoots and undershoots. It's much harder for exponentially growing populations to show this behavior, even though they do, and we'll explain why in a little bit. Okay, but the competition say, let's say the competition is the controlling factor. Competition increases at intervals here. It doesn't increase continuously. So you're not smoothly applying the brakes the way you are here. You're stomping on the brakes a little bit, stomping on the brakes after an interval. And in the meantime, you have hit a brick wall because you didn't stomp on the brakes. Okay, so you overshot. And that's going to cause then a die-off, which will then cause a crash. So discretely reproducing populations are inherently vulnerable to this. And depending on how big the population growth rate actually is, depending on the size of lambda, that will tell you how big the overshoot is going to be and how big the following crash is going to be. The bigger the value of lambda, the bigger the overshoot and the bigger the crash. And that has consequences. Here is how discretely reproducing populations behave depending on their growth rate, lambda. So if you have a lambda that is between, say, 1 and 2, so the population is growing, but not quite doubling every interval, you actually wind up getting a smooth approach to carrying capacity. It's close enough that you don't overshoot, really. And this is the mathematics. This is plugging these numbers into the growth equations. If lambda is between 2 and 3, that is doubling and tripling the population every interval, then you get overshoots and declines, but they tend to dampen out. They die out over time. You gradually approach your carrying capacity. If your lambda is between tripling and an increase of 3.57, which is kind of a mathematical breakpoint, then you get stable limit cycles. So these sine wave looking things we call limit cycles. So you get an overshoot and an undershoot, overshoot, undershoot. Basically, you're never at K. You're either above or below, above or below. And that's because you're reproducing much too quickly to slow down. So you overshoot and then you have a big die-off. But if your lambda is near 3, so it's not too much over 3, you get stable limit cycles that have 2 foci. You have 1 overshoot, 1 undershoot. As you get closer and closer to that break point, 3.57, it gets more complicated. You go from 2 stable numbers, as we've diagrammed here, to 4. So 2 above, 2 below. As it gets closer to 3.57, you go from 4 to 8. And then from 8 to 16. And then when you hit 3.57, you get what we call chaos. Okay. And this is where chaos theory comes from, actually. Is partly an outcome of modeling the growth of extremely rapidly reproducing populations. So what I've done here is just use the same graph as in density independent fluctuations. But what I'm trying to do is make the point that when you get to a population growth rate, a lambda of 3.57 or above, you get what looks like totally random fluctuations again. However, this is not totally random. This is generated by plugging numbers into the geometric growth equation. So you get these huge overshoots, and then you plug those numbers into the population growth equation, and you get then a huge crash. So this is deterministic. It's not random. It comes right out of the population growth equation. It looks random, but it's chaos. Chaos is not random. Chaos is mathematically deterministic fluctuations. They look random, but they're not. So when you see a graph that is wildly fluctuating like this, you now know that there are two possibilities. Could be chaotic fluctuations of a geometrically growing population, or it could be that this is due to density independent factors. And so you can't tell just from looking at the graph. You have to, if I give you a problem like this, you have to look into what the problem is telling you and see if you can separate the two. Otherwise, there are two possibilities. And you know that lambda has to be big. It has to be over 3.4. Now, notice that we have said, well, okay, you can get a lot of variation in geometrically growing populations. We haven't said anything about exponentially growing populations. At the moment, the only thing that exponentially growing populations can do is grow smoothly to K. They can't fluctuate according to the logistic growth equation, and they can't go extinct. What's really interesting about chaos is that there are populations undergoing chaotic fluctuations that can go extinct. So we've solved a lot of problems for geometric growth, but there's a lot of problems for exponential growth that we have not got a satisfactory answer for. So that's what we need to do now. So geometrically growing populations can have these fluctuations over here on the left, blah, 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 overshoot and crash. But exponentially growing populations can't do anything but approach K. So we have to solve that problem because we know that they can fluctuate. We know they can go extinct. All right, so time lags are an important reason why both geometrically and exponentially growing populations may show fluctuations. And time lags are difficult to get your head around. So let's take a minute to try to figure this out. In the population growth equation, we have like dm dt equals r times n, right? And it's the current n. And when we convert that to the logistic equation, all the n's that we're talking about are the current numbers. But if there's a time lag, then population growth is not dependent on the number at the current time. It's dependent on the number that were in existence at a previous time. So maybe 6 months before. That's what's determining your current population growth rate. So this is sometimes called delayed density dependence. And there are two reasons, well, there are a couple of reasons why you might see delayed density dependence. First off, if organisms store energy for their use, then they may have greater ability to reproduce at a later time than you might expect based on the population density. If 6 months prior, they were fattening up and storing energy, then what's really important is how competitive conditions were 6 months prior. And they may be able to reproduce way more currently than you might expect, given the density of the population now. Okay, so prior competitive environments can really strongly influence what's going on currently. And unless you know what happened 6 or 8 months before or 2 years before, you may not be able to model this population adequately. So a good example is that deer reproduce in late spring. Okay, but winter is really hard, right? And we know that deer die over the winter. And what really matters to the deer is not how many individuals there are in late spring when they're trying to reproduce, but what the competitive environment was like the previous fall when they were trying to fatten up. So was there a lot of competition in the previous fall? If so, they may not have been able to store a lot of energy, and they may be able to reproduce relatively little compared to their current numbers. On the other hand, if competitive environment was pretty lax in the previous fall, 6 months before, they may have a whole lot of energy to reproduce. They may reproduce way more than you expect. So here's some examples of what delayed density dependence does for continuously reproducing populations. So these are tiny organisms. These are Daphnia. And so here's Daphnia galatea up at the top. And it's a continuously reproducing organism. They have no season. And yet look at what's going on. They have exactly the kind of fluctuations that we modeled in discretely reproducing populations. Why is that? Because they store energy. So the competitive environment before the reproductive period is what's important to these guys. And so if they store energy, then the individuals that are experiencing a low competition environment can reproduce massively. On the other hand, the ones that are experiencing a very highly competitive environment can't reproduce a lot, and their reproduction falls off dramatically. So look, you get the kind of what looks like damped oscillations that we'd see in a discretely reproducing population. Okay. Here's Bosmina longirostris, which is another water flea type thing, and it doesn't store energy. So its current energy stores are determined by the current competitive environment. And look at its population dynamics. It rises smoothly to a carrying capacity. There's a small overshoot, but look, it's much more stable around a carrying capacity because there's no time lag. The previous competitive environment doesn't matter to this guy at the bottom. The previous competitive environment does matter to the one on the top. So here's another example of delayed density dependence. Okay, sheep blowflies, which very attractive. Yeah, you just feed them hamburger, and they have population cycles. Now, what happens here is that you can either feed them a fixed amount of food as larvae, or feed the adults an unlimited amount of food. Okay, so feed the larvae a fixed amount. Okay, and what that causes is these really wild population crashes. Okay, so you got a lot of adults that are breeding tremendously, but then they produce a whole bunch of larvae, and there's not enough food for the larvae. So most of the larvae starve to death. And that leaves only a few left to produce the next generation of adults. So you get then these wild fluctuations. Here, the larvae are all starving, and there's only a few left to produce adults. They produce some adults. The adults have unlimited food. They produce a gazillion larvae, and then those larvae all starve to death, leaving only a few to produce the next generation. If you do the opposite thing, if you feed the larvae a lot of food but limit the adults, look what happens. You get much less in the way of fluctuations. And that's because you're allowing a lot of adults to survive, a lot of organisms to grow to adulthood, but you're not letting them reproduce massively because food for adults is limited. So you may have a lot of adults, but they can only produce a few larvae. So there's much less of an effect. It eliminates the time delay. And when you eliminate the time delay, you get a much more stable population. So time lags can cause population fluctuations, even in continuously reproducing populations that grow exponentially. So how do we write an equation that looks like that? Well, okay. So you'll remember that we had dn dt equals r times n times that factor, okay, k minus n over k, or 1 minus n over k, because that's the same thing. So instead of n being the current n, we use the n at some previous time. Okay, and tau then is the lag. So tau might be 0.5 if it's a 6-month delay. So if what was important 6 months ago is what determines how reproduction is currently, then the current individuals, which are right here, our current population size, its reproduction is not determined by this. It's determined by the number 6 months previously, the number at time t with a 6-month delay, so 0.5. All right. Now, I'm not going to ask you to do any calculations with this, but I want you to know what the effect is. The longer the time lag, the more likely it is you'll get fluctuations. So if you have a short time lag, okay, and it's usually expressed as r times tau. So if r times tau is relatively small, you don't get any oscillations. You don't get any fluctuations. It's just a smooth approach to k. So a small time lag can still produce a smooth approach to carrying capacity and no fluctuations. If the time lag increases, though, then, hey, you get damped oscillations exactly the way you did with a discretely reproducing population. And if the product of r times tau is large, okay, then you get stable limit cycles. Again, just as you would in a geometrically growing population. So the longer the time lag, the more likely it is to get fluctuations, and the stronger the fluctuations are. The higher they go and the lower they go. Okay, but notice that we haven't said anything about extinction. You don't get extinction even with time lags in a continuously growing population. So we've solved almost all the problems, but we haven't solved them all. We know that continuously growing populations can go extinct. We just haven't got a model that allows that yet. So we have one more job to do. Okay. So let's summarize time lags. Time lags cause both kinds of populations to have fluctuations. Okay, and all I did was show you the continuous version. And that's because you get the point. We don't have to show you both. This is not an advanced population biology class. Okay, but we can't get chaos, we can't get random drift, and we can't get extinction from time lag models. And that's a problem, particularly for continuous reproduction, because we know that they do all of those things. Extinction is possible for discretely growing populations if you have chaotic fluctuations. But so far, it's the continuous population growth that's still kind of lacking. So, yeah, let me move this down temporarily. Go down there. Further. All right, so we'll put it down there for a second. Stochastic effects, that is random fluctuations, can cause extinctions in small populations. And now, what are we talking about stochastic effects? Didn't we talk about random fluctuations already? Didn't we talk about chaos already causing extinction? What exactly do we mean by stochastic effects? There are two kinds of stochastic effects. One is already familiar to us, and that is density-independent factors. But that's not the only thing that's going on. Okay, I'm going to move this back to the top so we don't obscure our graph. We're going to start our discussion of this by looking at populations and how the size of the population affects the extinction probability. So notice that small populations are more vulnerable to extinction than large populations. Here are the Channel Islands in California. They support bird populations of different sizes. The tiny islands support small populations. The big islands support big ones. Okay, well, here's the probability of extinction in a given year. And here's the population size. Notice that big populations have a very small probability of extinction. And small populations have a really big probability of extinction. Okay, why is that? Here's why. Oop, and of course, now I have to get my advance arrow. Okay, this is kind of, you know, kind of a problem for us because we normally think that little r, the population growth rate, should be really high in small populations. And so they should rapidly escape the small population size. They should rapidly grow. Well, we know that there could be Lee effects. So that's, you know, that's a possibility. But there's another possibility. And that is random variation in the life table parameters. We have treated the life table as deterministic, that say survival rates have a fixed value for any given age class and reproductive rates have a fixed value. But what if it's not fixed? What if it has a mean and a variation? So that when we say the survival rate of 3-year-olds is 0.4, so S sub 3, the probability that they'll survive to the age of 4 is 0.4. Well, what if it's 0.4 plus or minus 0.3? It could be as high as 0.7. It could be as low as 0.1. Well, what if you get one of those bad years where the survival is 0.1? What will that do to the population? Well, this is random, right? You're rolling dice to determine, hey, just randomly, what's the survival rate going to be this year? If you roll snake eyes and you have a very low survival rate, the population is going to decline. Even though you've got pretty good reproductive rate. It's going to decline because the survival rate has randomly fallen. That is what we call a stochastic model, where the values in the life table, the value of R has a mean and it has a variance. So it could be much higher than our mean value. It could be much lower than our mean value. All right, well, what does stochastic population growth then look like? Okay, well, let's compare a deterministic model that comes right out of the life table where the values are fixed to a model where we're randomly sort of using a computer to roll the dice on which value for survival and reproduction we get. Well, the blue line is our exponential increase. On the other hand, this red line is one of the many possible stochastic outcomes. So on average, the population will follow an exponential increase. Okay, so on average, this is what it should look like. But any given population may look very different. This is that random wandering that we've been unable to model so far. And notice that if you get stochastic variation where you roll the dice, say 3 years in a row, and you get snake eyes each time, you get extinction. And that hasn't been possible in any of our models for continuous population growth so far. So stochastic population effects, that is random variation in survival and reproduction, random variation in the population growth rate, little r, can help us model the most difficult situations we have in nature. It can allow us to have continuously growing populations grow variably, they can fluctuate, they can even go extinct. So when you see continuous population growth and it's not growing continuously and approaching K smoothly, that's a tip-off that one of two things is happening. Either you've got a time lag or you may have stochastic effects. If you've got time lags, a continuously growing population will show those regular fluctuations. But if you get extinction, if you get wandering paths that aren't regular, this is an irregular path, you're almost certainly dealing with stochastic effects, random variation in survival, in reproduction, and in little r, the population growth rate. Now, there are two kinds of stochasticity. There's demographic stochasticity that I've been talking about in the life table. There's also environmental stochasticity. Environmental stochasticity is basically very much akin to density independent factors. And I won't press that point. I'm going to focus more on demographic stochasticity, that is variation in the life table parameters. Okay, so let's just look at what happens to the extinction probability if you have a string of years with low birth rates or high death rates, and you see that the probability of extinction here is pretty related to the population size. Okay, so your population size is low. All you need is one bad year, and you're very likely to get extinction. And the reason you don't see the green line is because it goes up to 1 right here. Okay, larger populations need much more in the way of bad years to force them to go extinct. Normally, large populations have a relatively low risk of extinction. But the smaller the population, the higher the risk of extinction at any given time. All right, now last thing is we can estimate the probability of extinction. If you're growing stochastically, this is one of those random processes that we can model just using mathematics. Okay, so the probability of extinction, if you are growing stochastically, is the death rate divided by the birth rate, D divided by B, raised to the n power, where n is the population size. So if your birth rate is 0.4 and your death rate is 0.3, well, that's 0.3 divided by 0.4. That's 0.75 raised to the power of how many individuals are in your population. You got 10 individuals in the population, it's 0.75 to the 10th power. If you've got 100 individuals, it's 0.75 raised to the 100th power. Remember, this is the probability of extinction. So it's really clear that that probability goes way, way down as your population size increases. But now this has some really interesting and counterintuitive properties. Because let's look at a population with size 10. And let's look at a low death rate and a low birth rate. So the birth rate is bigger than the death rate, right? Okay, so The probability of extinction for this population is 0.1 divided by 0.2 raised to the 10th power. Well, this is 0.5. 1 divided by 2 is 1/2. So it's 0.5 to the 10th power, and that is 0.00098. So it's about 1 in 10,000. There's a 1 in 10,000 chance that a population with these birth and death rates will go extinct in a given year. So hey, that's not terrible. It's 1 in 10,000 chance that you'll still have 10 individuals next year. But let's look at a higher birth rate and a higher death rate with the same population size. Okay, now 0.4 divided by 0.5 is 0.8. 0.8 raised to the 10th power is 0.1. You have a 1,000-fold higher probability of going extinct if your birth rates and death rates are higher than if they're lower. Okay, why is that? Well, it's because if you've got random variation in a high birth rate and a high death rate, the death rate could go way up in a given year. At the same time, the birth rate goes way down in a given year. So it's inherently more variable. So high birth rates and high death rates are associated with a higher probability of extinction for a given population size. This is cool, but it's also kind of frightening because the relative difference in birth and death rates is what's important, not the absolute difference. In both of these examples, the absolute difference was 0.1. The birth rate was 0.1 greater than the death rate. And that sounds really good. But the relative difference is what matters. In the first population, the death rate was half of the birth rate. The second population, the death rate was 80% of the birth rate. So randomly, you can get much higher death rates associated with crashing birth rates more easily in that second population. So this is the one calculation that I will expect you to remember. Just remember that equation. The probability of extinction for stochastic population growth is deaths divided by births raised to the power of the number of individuals in the population. It's pretty simple. It doesn't require a lot of practice. So just remember that one. And everything else in this presentation is trying to relate ideas to the graphs that are trying to depict those ideas. We see populations do a bunch of different things. They can fluctuate, they can be stable, they can fluctuate predictably or unpredictably, they can go extinct. And what is associated with those things? Is it density independent factors? Is it the relative population growth rate for discretely growing populations? Is it a time lag? Is it stochastic population growth? What concept goes with what graph? That's the key for today. And you'll get one of these graphs on the exam. And I'll be asking you what concept is likely to go with this, or maybe what concepts, if there are two different things that could explain that. So you'll have to look at the question. You'll have to say, is he talking about discrete population growth, or is he talking about continuous population growth? Because that will eliminate some of the possibilities. And then you'll have to explain what is likely to be responsible for the behavior of the population that you see depicted in the graph. Okay. Do we have any questions about this? It's going to take a little time to digest. I want you to go back through this PowerPoint and try to link the concepts with the graphs. That's the key thing. Yeah, I will give you a stochastic population extinction question. It'll be worth maybe 4 points because all you have to do is plug it into your calculator. So just so that we know that you know how to do that. But it's much more challenging to keep the concepts straight and to link them to the dynamics of the populations. So that's going to be an important task for you. And remember, our exam is on Friday. So don't delay. Go back and start reviewing right away. Questions here? Questions at home? Oops, and I'm gonna gotta stop sharing here. Okay. All right, if there are no questions at home and you typed in after we got it recording, then you are good to go. You guys are good to go here. Good luck. Have a good rest of your weekend. I'm sorry that we had to do this. I'm sorry for a lot of things related to the storm, believe me. And I will see you on Monday. I got a doctor appointment at 8:30 that morning, but man, I should be here at 11.
Thank you.
Thank you.
All right, guys, at home,
Thank you.
speak up or log off.